So we're given a matrix in B1, we're given a matrix and we're asked to use elementary row operations to determine if A has an inverse. If A has an inverse, provide the inverse. If not, provide an echelon form of the matrix. We're told how we have to determine if it has an inverse. So while we're going to learn the determinant tomorrow, if we're told you have to use elementary row operations, it's forcing a specific type of technique. So the way that we know at this point how to determine if it has an inverse is we set up the system of equations like so, or we set up an augmented matrix like so. Sorry, not a system of equations, but an augmented matrix. And now from here, what we're going to do is we're going to do elementary row operations to convert this into echelon form. If the echelon form, if this becomes the identity in the echelon form, it's invertible. If it doesn't become the identity, then it's not invertible. So let's take row 2, subtract 2, row 1, subtract and replace row 2, and we'll take row 3, subtract 3, row 1, and replace row 3. When we're doing these subtractions of rows, if we're using one entry to eliminate the other rows, we can do the elimination all at the same time. We can use row 1 to eliminate the entry in row 2 and row 3 at the same time. So row 1 doesn't change. Now here this becomes 0, 1, minus 1, minus 2, 1, 0. This becomes 0, 1, minus 2, minus 3, 0, 1. And now I'm going to take row 1, subtract row 2, subtract row 2, replace row 1, and row 3, subtract row 2, replacing row 3. This gives me 1, 0, 2, 1, minus 1, 0, 0, 1, minus 1, minus 2, 1, 0, and 0, 0, minus 1, minus 1, 0, 1. Now I'm going to take row minus 1 times row 3 to replace row 3 to give me 1, 0, 2, 1, minus 1, 0, 0, 1, minus 1, minus 2, 1, 0, and 0, 0, 1, 1, 0, minus 1. And now row 1 plus minus 2 row 3 replaces row 1, and row 2 plus row 3 replaces row 2 to give 1, 0, 0, minus 1, minus 1. I subtracted 2, so this is going to be minus 1, minus 1, 2. And now 0, 1, 0, minus 1, 1, minus 1, and 0, 0, 1, 1, 0, minus 1. So as this, A equals the identity, M, or as A prime equals the identity, A has an inverse. And the inverse is the matrix minus 1, minus 1, 2, minus 1, 1, minus 1, 1, 0, minus 1. And that's our inverse. Okay. If we got to this point and this matrix here was not the identity, it was some other echelon form, then because the echelon form is unique, there is no way to convert it to an identity matrix, meaning that the matrix is not invertible. And we would simply provide the matrix that we got over here as our justification. Okay, now we have a linear transformations from polynomials of degree at most 3 to the real 2 by 2 numbers, and we've given this notation here, which means that we're going to plug 3 into our first linear transfer, our first function, and for our first entry, and we're going to plug -1 into the function for our second entry. So now what we're going to do is we're going to take this linear transformation, which looks a little bit confusing, and we're going to turn it into T alpha beta, because we like using T alpha beta. So what we're going to look at is we're going to look at what does T do to 1? What is T applied to the vector 1? Well, that's going to equal f. If f of x equals 1, then f of 3 equals 1, and f of -1 equals 1. So this is going to be 1, 1, which equals 1 times 1, 0, plus 0 times, or 1 times 0, 1. What about T of x? Well, f of x equals x, then f of 3 equals 3, and f of -1 equals -1. So this equals 3 minus 1, which equals 3 times 1, 0, plus -1 times 0, 1. What about T of x squared? Well, if f of x equals x squared, then f of 3 equals 9, and f of -1 equals 1. So this is going to equal 9, 1, which equals 9, 1, 0, plus 1, 0, 1. Taking these together gives us that T of alpha beta equals 1, 1, 3 minus 1, and 9, 1. So that is our matrix. Now we're going to use this matrix to compute the kernel. Now the kernel, we're going to consider ATV1 plus BTV2 plus CTV3 equaling 0. Here, this gives us a system of equations that's represented by 1, 1, 3, -1, 9, 1, 0, 0. And this represents our system of equations. Okay? Now, from here, we're able to solve this system of equations by taking R2 minus R1 gives us, replacing R2 to go 1, 3, 9, 0, 0, -4, -8, 0. Then R2 times -1/4, placing R2 to give us 1, 3, 9, 0, 0, 1, 2, 0. Now R1, R1 minus 3R2, replacing R1, gives us the matrix 1, 0, 3, 0, 0, 1, 2, 0. And now let A, B, C be a solution to A T of V1 plus B T of V2 plus C T of V3 implies that A B, C equals, but what are our variables? Our variables here is that A and B are basic variables, and C is a free variable. So we got to figure out what A, B, and C are. Because C is a free variable, let C equal T, an element of the real numbers. So T is a real number, and now we have our system of equations. A plus 3C equals 0, and B plus 2C equals 0. Because we've let C equal T, this implies that A equals minus 3T and B equals minus 2T. Well, this implies that A, B, C equals minus 3T minus 2T, T. Now I can take those values for A, B, and C and plug it back into this expression we considered. So minus 3T, T of V1 plus minus 2T of T of V2 plus T of V3 equals 0. This implies that T of minus 3T V1 minus 2T V2 plus T V3 equals 0. And now we have a linear combination of elements. This implies that minus 3T V1 minus 2T V2 plus T V3 is in the kernel of T. And we have a definition for our elements of our kernel. Isolating for T, we get T times minus 3V1 minus 2V2 plus V3 is in the kernel. And now, for each basic variable that we have, we can group to create our basis vectors. So the kernel, in this case, is going to equal the span of the set containing this minus 3V1 minus 2V2 plus V3. But what is my V1, V2, and V3? If we look back, my V1 is 1, my V2 is X, and my V3 is X squared. So this is actually the span of minus 3 minus 2x plus x squared. And this is our basis vector for our kernel. So if we compute the kernel is the span of these vectors. Things to note: the dimension of the kernel, T, equals 1, because I have one vector here. And then if I wanted to know what the image, if I wanted to create a basis for the image of T, I would look at which values were my free variables, A and B, and I would take the output of T of A and T of B, which are here. So the basis for the image that I would create, the image equals the span of the set 1, 1, and 3, minus 1. And that's procedure 1.